PhD student from University of Modena and Reggio Emilia, and I'm glad to be here. And I thank so much the organizers. So I'm going to start from, I'm describing in general a microscopic model for local uphill diffusion. And I'm going to start from classical diffusivity equation. And that microscopically is the following. So where D is the diffusivity constant, and we assume that it is actually a constant. The domain we consider is 0, 1 in space and 0 plus infinity in time. And rho is the density of a species, and we assume that it is a smooth function and strong solution of the equation you see. And we assume that we endow the problem with Dirichlet boundary conditions. So what can happen if we add another species? So if we consider a situation where two species are present. Sorry, I forgot the mask. And yes, we might imagine three situations. The first one, it is called the decoupled case. It is decoupled because yes, we have two species, but they do not interact between each other. So they, in some sense, they have a diffusivity properties that are not interacting because there is no interaction term in the limiting equations. So here we always assume that rho 1 and rho 2 are two smooth functions, that they are the densities of the species, and we assume that we have a Dirichlet boundary condition and on the boundary of the domain, and we denote them by rho lowercase alpha 0 or 1, depending on the condition we are considering. The second case that has been studied by Floreani, Giardinade, and Hollander, Nandan, and Redding in 2021. It is called the weakly coupled case because the coupling, here we have two diffusivity equations that are coupled in a zero derivative term. That means that the coupling is in a so-called reaction term, and let us notice that this reaction term is conservative in mass. So the third case we can consider is the one we are most interested in, and it is called the strong coupled case because here the coupling is both in the zero derivative and both in the diffusive term. That means in the second derivative. So we can notice here that there are two more diffusivity constant, D12 and D21, that are called also crossing diffusivity constant because they, in some sense, cross the diffusivity actually because they multiply the gradient of the species that of the other species. So the question we would like to answer is, how can we define an interacting particle process that has the above cases as hydrodynamic limit? So let me remark some general facts. Consider a Markov, actually a Feller process on a discrete state space, and we can, as we know, identify it by its infinitesimal generator, that is, concretely speaking, defined by the transition rates from eta to c. And we also know the so-called master equation that describes the evolution of the expectation of a function that belongs to the domain of the generator in time. And let us remark that the expectation is it has been taken with respect to the law of the process initialized at x. So with these tools, we define a state space that is composed by the number 0, 1, and 2, where 0 mimic the empty state, 1 and 2 indicate the two species. So 1 it is the first species, and 2 it is the second species. We assume that the lattice we are working on is n, and it has dimension n, and it is finite. And so we use as a dynamic a so-called pairs dynamic, and it has been inspired by the work of Fuji and Wadati in 1997. Indeed, with such a dynamic, we have, by considering a pair of cites, for example, x and x plus 1, the transition that assume that these two cites have a configuration gamma and delta. The transition that occurs is carries these two cites in the configuration alpha and beta, where gamma, delta, alpha, and beta can be anything. So both empty states or particles, and among particles, they could be any species. So this transition occurs at a rate that we call W, lowercase gamma delta to indicate the starting configuration, and uppercase alpha beta to indicate the arrival configuration. So in order to obtain the result we are looking for, let us consider a function that is the indicator function of the event that for a fixed species, the configuration at time t and in the coordinate x is exactly alpha, so the species we have chosen. So in order to obtain the result, the limiting equation we would like to have, we are looking for a generator that, for which its densities acts on the indicator function in the way you can see here. So we have the first, we consider for simplicity just the first species, but similarly we can extend this computation to the second one. So here the action is a constant that is called diffusivity constant for the species 1 into itself, and multiplied by the so-called discrete Laplacian. So it is in some sense a center difference Laplacian of the first indicator function, in other words, a discrete Laplacian, and plus the crossing diffusivity term times the discrete Laplacian of the second species, of the indicator of the second species, sorry, plus a linear term that mimics the reaction part. Let us notice that here we do not want any constant term in the action. So similarly, as I said before, we can argue for the second species, and yes, in order to obtain such an action, we have to impose some condition on the transition rates, and the conditions we have imposed are the following. So first, we would like to have, as I said before, two coupled Laplacian and a conservative reaction term. So we surely have to impose this condition. The second, we would like to keep the linearity of the system. So we would like that the system is linear. And for this reason, we do not want a correlation of order greater than 1. We have to require that the generator we find is indeed a stochastic generator, a Markov generator in particular, and also, as I said before, we do not want any constant term in the action. So as a result, we have that in order to obtain such a kind of action, we cannot choose arbitrarily the physical constant. So in particular, the diffusivity constant have to satisfy the first constraint. So the sum of d11 plus d21 must be equal to the sum of d22 plus d12. And also we have a lower bound for the reaction constant. Furthermore, we find that there is two parameters family of processes that leads to the required action, and two parameters in the sense that the system that we have built up before by imposing the four conditions is underdetermined. I mean that we have more unknown than equations. and thus we have some degrees of freedom in some sense to use to discriminate these processes, and thus we have a family of processes. A remark, yes, the result we obtain is in agreement with something that has been already observed by Kahane in 1987. So that means the impossibility of having just a strong coupling without reaction. So we cannot have a system that is just coupled in the second derivative, but not in the zero derivative term. And so, and this is because if it happened, we would have negative transition rates, or if we consider a microscopic point of view, or by looking at a macroscopic point of view, we would have the violation of the maximum principle for the limiting equation. So let me give some concrete example. For the totally decoupled case, our process, the process that describes this totally decoupled case is the so-called steering process. The steering process is a process where the pairs of the configuration of the pairs of CITES is just exchanged. So we start from gamma delta and we arrive to delta gamma. So these exchanges mimics the coupled diffusivity equation. For the third case, I mean the strongly coupled case, a result we can find is a process that is a superposition of two simple processes. The first one is a steering that mimics the independent diffusivity, and to mimic the crossing diffusivity and the reaction, we have to add a so-called steering mutating process. That is a process that acts like that. So with rate 1, we have just the first steering. So we exchange at a more fast rate, and the other steering and mutating process is a process that is slower and exchanges the two CITES, and after that it mutates the two CITES. The mutation is defined through this map, a map that if we have one associated 2, if we have two associated associates 1, and if we have the empty site, nothing can mutate. So I would like to end up with the appeal. We know that the Fick's law says that the current of a species is proportional to minus the gradient of the density. And in the case of the two species, we have to write the currents of the two species by considering also the crossing diffusivity. Can we violate this law? By violating it, I mean that if we have density on the left that is lower with respect to the density of the right, if we follow the Fick law, we would have a downhill current, and otherwise, if we violate the Fick law, we would have an uphill current. An uphill current, it means that it has the same sign of the gradient of the density. So what we can define the global uphill if this violation of Fick law occurs in the total gradient. So the gradient that it can be obtained by summing up the flux of the two species, and where the density is the sum of the two densities. And we can define a local uphill if it happens just for one of the two species, say for the species alpha. What is the result for the model we studied? For the strong coupled case that is described by the steering mutating process, we cannot have a global appeal because of the constraint on the diffusivity constant. But we can have a local appeal that is carried out by For example, for the first species, by fixing the left density lower than the right density, and we can build up a situation where the current is positive. Its minimum is positive in its minimum in X is positive. So I carried out a simulation. We can notice here that for the first species, the density has a lower value on the right, on the left, and a higher value on the right. And but in this situation, the current of the first species stays always positive. So we have a local appeal phenomenon for this model. Okay. Yes.
Finish the conclusion.
Yes. Here just a comparison with the other model, but I can skip it for questions. So thank you for the attention, and I'm here for questions.
Is there any question?
Just a question on the initial system of PDEs. Did you try to use a coupling between a fundamental solution of the coupled heat system and the C term or not? That means use the PDE and not the discrete model. Did you try or to compare? On?
Do you mean for the appeal?
Yes.
No, the appeal it has been studied in a stationary state, so without the time dependence. So we just
so
solved
the time dependence. Did you have because I think you can derive an exact solutions to a fundamental solution of the heat equation.
Yes, we can.
So did you compare your calculations with this result on the continuous system?
I did it for the stationary case. So I actually solved the.
So I done that. So you did not. So that would be a good idea to do so.
Yes, it is an interesting suggestion. Yes, we for the moment we just studied the stationary case, but we can. It is a good suggestion to study also the non-stationary case. Thank you so much.
Okay, thanks. So we are a little over time, so I propose to stop here.